So we were looking at this sequence of functions. Okay. So let me begin with a question. Okay, let's try to do that question. It's not when let's we are doing this sequences of functions and uniform convergence. Maybe say uniform. Because maybe if we just get to a certain place in this, then we can move to some other topic. Right? Otherwise, it will be half done and then, yeah. So far, we have not done much solid. We did prove that uniform, if you take a sequence of continuous functions and you take and they converge to a function uniformly, and that place where they converge is also a continuous function. Okay, so that was certainly nice. Okay. But maybe we can do a few more things, and also a bit of practice. So here I want to understand the following. So suppose that you have this sequence of continuous functions. 0 to R. And let me not say that these are continuous, it's just functions like this. And let's say that these are converging uniform to some phi. And this is uniform. Now we have a function f, okay, which is continuous. So now I will try to denote continuous functions. I will denote continuous functions like this. So C0 means that we are not 0 times differentiable and continuous. There is a good reason for why this notation is chosen and so on, but let's take this. This just means continuous, collection of all continuous. Then this is then show maybe show, but is f of psi I also uniformly convergent. Okay. So let's try this. So you can understand that this is also a sequence of functions. So is this sequence of functions? Now these are also functions on C0 comma on 0 comma 1. Okay. Yes. So by the way, there is a small problem. Okay? There is, I mean, f is not in C0 comma 1. That is not correct. So can anybody say why f being in 0 comma 1? If I say, well, what is the problem? So there is a set theoretic problem if f is just defined on 0 comma 1.
Yeah, there is this, like, it's a composition of function, right?
Yes.
f of psi I, and psi I value might not be in 0, 1.
Yes. Right. So that's why it's not a good thing to put it like this. And yeah, so maybe just say from R, it's just continuous on R. So Raghav, is that point clear? That's just about composition. You will not be able to take the composition.
No, sir, I didn't understand.
Right. So you see, what you're doing is f of psi 1. Okay. But suppose that psi 1 of half is 2. Then is it defined? Is f of 2 defined? No.
No, no, no.
If f was on 0, 1. So that's why it's not enough to say that f is defined on 0, 1. Right? F has to be, because we don't know the range of psi I, because that's going to be have to be contained in the domain of f. And so we just take the domain of f to be all of R. So
Okay.
that's the question.
I got it.
Okay. Another question. Okay. Can anybody tell me an analog of this for the real, for the case of sequences of numbers? Because again, that's our whole goal. We want to understand sequence of functions by studying its analog by just comparing it with sequence of numbers. So can anybody point out an analog to this in sequence of numbers? Here we have a sequence of functions. Psi I is a sequence of functions, but is there an analog in sequence of numbers?
Sir, so what would such an analog look like?
What will such an analog?
I mean, what will, I
Is
mean,
it the
Wait, so Raghav, can you complete just a second?
no, so what do you want us to define? I didn't understand.
Yeah, that is a little vague, but it's like what I'm saying is that if this psi I is a sequence of functions, then I'm asking you if this is true or not. But what if this is a sequence of numbers? This is maybe that was Adish. So Adish, you were saying?
so wait. So I was saying that if psi I is a sequence of numbers like psi 1, psi 2, psi 3 are,
Huh.
is that phi or is that psi?
Anything. Sorry. It is phi. I've been saying psi, but that's obviously wrong. It's phi.
Yeah, so phi 1, phi 2, phi 3 are numbers. That is just that. So this is uniformly convergent, means that this limit will exist, f of
Yes.
phi I, and that is like just sequential criterion
On continuity.
for on
Yes.
continuity.
Yes. Right. So Raghav, do you see what he said?
No, sir.
Adish,
I-
explain again. Yeah, explain it more clearly.
Yes, so basically continuity, so basically we define any kind of limit. We can define any kind of limit by also considering uh, sequences, because sequences are also like special functions from N to R. We define them, and for continuity we say that, for example, if we want to prove if this fact holds that limit of f of x as x tends to c is some f of c, and obviously this fact also holds that for any sequence which of numbers which converges to c, the sequence of f of xi, those xi numbers, will converge to f of c. So this is the
Right.
similar thing. So if
Yeah.
this is converging, then it's just checking the continuity.
Right.
And obviously the uh, right to left result also holds, like,
Yeah, that's right.
for all sequences.
Uh, I mean, if for all sequence happens, then it's continuous, right?
Yeah, that is.
Huh. That's right. That's correct way to say right to left. So basically from here to here. So now Raghav, is this?
So he's comparing this with the limit.
Yes, with the limit in the case of numbers. Okay, like if these psi i's are numbers, okay, if you imagine these psi i's not to be functions but just numbers, okay, then
got
these
it.
numbers, right? Yeah, and this sequence of numbers is converging to somewhere. Then if you f of them will converge to f of the number, and so this will be convergent. So you see, basically that is a result which is true for numbers. Now we are asking if the result is true for when psi i's are functions. But the convergence that we have is a strong form of convergence under uniform convergence. Under pointwise convergence, we are not asking this. We don't even expect that it will be true. Will it be? Okay, I mean, okay, so I'll just take that thing back. It won't be true. We are not, I'm just saying we're not asking it in the case of pointwise convergence. We're asking it in this case of nice convergence. Okay? And this is what we have seen so far, right? That if
But
the
then if-
convergence is nice, like if this is uniform convergence, then a lot of properties that happen for sequence of numbers also hold for sequence of functions. Yes, Adish, go on.
But why aren't we asking for pointwise convergence? Because if, first of all, if we study pointwise convergence and for some case it does not happen, then obviously uniform convergence will also not happen.
That's right. So in fact, one can ask that and should ask that. So that's right. So why we are not asking, the answer to that is that we should ask. Okay. Okay, but why I did not ask is because usually pointwise convergence is not useful because the limit is not continuous. In the sense that the limit, yeah, this limit is not continuous, right? And so the limit will not be in the space of continuous functions if let's say psi I was continuous. And suddenly you will go out of that. And that's why it's not very interesting. And yeah. So this question came in a proof of certain differential equation, some Picard's theorem, which maybe I'll say for a minute after this. That's why I came. But yeah, one should ask that. Okay. Yeah, and in fact, if you ask it, then the answer is yes, right? If you replace this by pointwise convergence, the answer is yes. Just check. It is easy. You ask this for pointwise convergence. So do this first. Do it for pointwise. So we are just asking if this is pointwise convergence, right? So you take a x naught and try. It should be clear whether it's possible or not. Immediately. Should we do the pointwise thing? Let's do it. It's just a matter of getting comfortable with this. So let's just pick a.
So basically, we need to prove that there exists a natural number n after so basically there exists a natural number n after which if we take the i's greater than that natural number n, then f of phi I minus f of phi, that modulus of that must be less than some epsilon.
for any fixed x naught, if you're doing pointwise
Yeah.
convergence, right?
Fix it.
But that is absolutely trivial, right? Because when you fix the x naught, then it just becomes a sequence of numbers again.
Yeah, is that a notation, composite function notation?
Which notation? This one?
This no, the one you wrote below it, just below it.
I don't. Okay, this is just x naught applied to this function f compose phi.
So it is f of phi 1 of x naught, right?
But that's the same thing, right? It's
No, it just looks like multiplication to me right here. That is why.
oh, okay. Yeah. So we are doing this. Yeah, maybe more better to write like this.
Yeah.
Yeah, correct. But it's the same thing. Yeah. Does this converge? And of course this converges, and this just converges to f of phi of x for every x naught, right? Because what is this situation? This is just like we have this numbers, because function composition, right? So you can just apply psi. That's the meaning of composition. You apply phi 1 first, and you look at this, and this converges to phi of x naught. That's given to us. That's the hypothesis of pointwise convergence. And then you're just applying f. And again, these are numbers. That's what we just talked about, right? These are numbers. And so if you apply it on these numbers, this will converge to this. Because f is continuous, it will, when you apply it to a convergence sequence, give a convergence. If it's not clear, then please say. Okay, so then I assume it is clear. This should be clear. If it's not, then you should say. So then we move back to our.
So by this, can we answer those questions like which we weren't unable to answer like last year or something, like when we take limit of log of something, then we can easily pass it over to the inside bracket. Like we can pass over the limit to the, for example, if we take log of x square plus x plus 1, then maybe we can pass the limit to x square plus x plus 1, log of limit of x square plus x plus 1. So now does this theorem basically facilitates the exchange, like passing over of limits inside the function? Because if you see, log is continuous.
No, but this passing the limit is just following from the fact that it is continuous. This has nothing to do with, I mean, you don't need at least to say use sequence of functions. See, this is just the definition of continuity. I mean, this is just the definition of log being continuous. Right?
Yes.
Yeah, it just follows from log being continuous that you can push the limit inside.
Right.
So maybe it is a good exercise, but just to do the epsilon delta proof, always as much as you can do, you should do epsilon delta proof. Basically, if f is continuous, g I'm not saying is continuous. If f is continuous, then you can, then this limit is equal to this, basically the limit and this commute. All good things can be stated in terms of commuting. That you can take as a theorem, sort of meta theorem. All good things can be stated in terms of commutativity. Anything you learn in math, okay, homomorphism, homeomorphism, okay, not homomorphism, anything in group theory, linear algebra, everything can be stated in terms of a commutative. Okay. So this will happen if f is continuous, and obviously the limit has to exist. This limit has to exist, otherwise it doesn't make sense. G is not assumed to be continuous. Prove this, take it as a problem and just do it at home, okay, after the class. All right. So now let's so you note it down. Let us come to the real question. We are avoiding. Should I say avoiding? No, we are not avoiding, but yeah. Let us come to the real question. This is also equally simple. But yet, a lot of people yesterday we were doing this in the class, some differential equation, this part in the proof on Friday, I think, and a lot of people got confused. I also got confused. Many people got confused.
In the
In our MMath course.
first year. Okay.
Yeah. No, so it was not basically. It was not pure properly written like this. It was a part in something, and obviously it was from some n-dimensional space and so on. So that was probably also a source of confusion. But and then the teacher just said that no, it's not. You don't need. Just said it's compact. She just saying compact. She did not say that it's due to this. Anyways, maybe from there also it follows because it was some integrals that were involved. So you don't need uniform convergence to exchange integral elements. Those things we will see.
Just give 1 minute.
Yes. Yeah. So just think about this.
I think it's not that difficult to do this
Okay.
because if once we prove pointwise convergence, I think we just have to follow from that, extend on that pointwise thing.
Okay. How?
So, like we just have to prove that now the value of n does not depend on x
Right.
for uniform convergence.
Yes.
And but as in pointwise convergence, we treated uh, f of phi I of x naught as a sequence of numbers.
Right.
So similarly, maybe we can keep x as arbitrary,
Mhm.
but like it's obvious, right? Because f of phi I is converging to phi uniformly. So for
Phi I is converging to phi uniformly. Right.
so basically, and we know. No, wait, I made a mistake in my argument. I just realized.
When you when we are done with this, you will see it's obvious. We are just not comfortable with.
Right now also I am feeling that like that it should be obvious, but the arguments
So you
have
try
to
make
construct
that.
them properly.
So let us write what this uniform convergence I n x minus I n is less than epsilon, right? For all n bigger than some n. And for all. This is the definition. Raghav, this is the definition. You agree? Yeah. Okay. Hello. Raghav, this is the definition. You agree? What happened to him? Anyway.
Hello, sir. My
Yes.
network. What happened? What were you telling?
Oh, no. I'm just saying. So we are trying to prove this result, right? So I'm just saying that I've just written the definition of uniform convergence. Is this fine?
Yes, sir.
So try to use this. Now, this is what you have written. This is what the definition is. And here you want to show that. Here you want to show that this is less than, and so obviously the limit you can guess it's just this, right? You want to show that this is less than, let's say, epsilon 1, given epsilon, yeah, given epsilon 1, you want to show this for all n bigger than some, n naught or whatever, and for all. This is what we want to show. And f is continuous. So how do you use the continuity of f?
Sir, like that previous idea can we use? Can we pass the limit over to inside?
Pass the limit. Basically, see, that is the question that we are asking. Can we pass the limit to inside? Right.
Yeah, because that is why I asked you the previous question that
No.
that log 1.
Okay. No. That is
Like
fine.
if we prove that, then obviously that is also proved.
No, but there the function was fixed. No, here we have a sequence of functions. There the inside function gx was only one function, and you pass the limit inside. But here there is a sequence of functions.
No, but this is a much more stronger generalized result than that thing. If we prove this, then that is obviously
Oh yes,
sub case of
yes,
this.
yes. That's right. I mean, okay, if you prove this, then obviously you can take phi a to be constant sequences, and then the thing about real numbers is
That's
also.
why I was asking that if we prove this, then is that result like that
Yes,
is another.
yes, yeah. Because it becomes a constant sequence.
Sir, then let's just break this inequality. Phi n of x will be greater than phi of x minus epsilon and will be less than phi of x plus epsilon.
Right.
Now f is continuous, so if we take the function now to three sides, so what can then we say about the inequalities?
That will not be
Nothing.
preserved. It's not increasing.
Yeah, that's what.
But if two things are close enough, then f applied to them is also close enough. That is continuity. Right? You can use that.
Yes. Yeah. Mhm. Okay, so maybe we can say that we can obviously say that as f is continuous,
Mhm.
okay, as x is continuous, mod of f of u minus f of phi of x, that should be less than epsilon for
Mod
a
of
given. Yeah,
okay.
I'm just keeping this u as a right now something, because phi of x is some number, right? Phi of x is some number.
Right.
It's x.
For all what?
Uh, for all u belonging to some delta band of phi of
Yes.
x.
Yeah. Right. That's so. This is just the definition of continuity. Okay. Phi of x is just a number. If you treat x as fixed for phi is just phi x is a number. So this okay.
But now, can we, like in the above definition, now can this epsilon be this delta? Like, can this be a band? Like for example, now we consider in this definition above phi n of x minus phi of x, this is less than epsilon. This will be less than delta for some n, right? That is true.
Okay. So this is less than delta for all
Delta for
n.
some n.
Right.
For some n greater than n naught. And now we can say, right, uh, that obviously phi n will belong to this band.
Right. Phi n. Yeah. So phi n is inside this, right? So that's phi n is inside this, right? Okay.
Yeah, then.
That's correct. So then
Yeah,
we
then we are
get
done,
this.
right?
But there is
We are
still a
fixing
problem.
the x right now.
You're fixing the x and doing all this.
Yeah.
So let me say
But
the
we are
argument.
keeping the x's are arbitrary, right? So it doesn't matter.
No, it matters. The this delta depends on x.
Oh yeah. That
Right.
is also.
So I mean, so far.
But then, but yeah, this
So,
continuity delta is dependent on x, but this delta in uniform convergence, but that is the same delta we take. So that is also dependent on x. But n is not dependent on x.
right. No. So no, that's right. The n is not dependent on x, but the sorry, 1 minute. I'm also getting confused. So if you fix so if you want this to be less than epsilon, then you will have a delta, which will depend. Yeah. So let me say this from beginning here. So first of all, I mean, if we just try to do just a proof, maybe a wrong proof sort of, okay. So the point is that you have a phi x, okay, phi x and then this phi nx, right? You want to, that these two will become close to each other if n is large enough, okay. Oh God, there's less than 1 minute left. Okay. Yeah, so let's discuss this on the other side. I will just open this board and do it from here. Okay. I'll just save this. Okay, just join once again. That's it.